So in Chapter 3, Section 9, we're going to be discussing the topic of related rates. So the idea of a related rate is, well, rates are slopes, and we know that slopes are derivatives. So the idea is, if we know the derivative of one function or one variable, can we use this to determine the derivative or the rates of change of other variables? This turns out to be very useful in many sciences because oftentimes it is impossible to directly measure certain variables, as we will see in some of our applications. So it allows us to figure out the rates of certain things based on the rates of other observable quantities. So we're going to start with a summary of our technique to resolve related rates, and then we will apply this to a bunch of different situations. So as with any application problem, we always want to read the problem carefully. With these ones, oftentimes there's going to be a geometric component. So drawing a good diagram is a very helpful thing. In our diagram, we need to introduce notation and assign symbols to all quantities that are going to be functions of time. So since we're talking about related rates, almost always these quantities are going to be changing over time. So anything that depends on time needs to have a symbol assigned to it so that we can later on take the derivative with respect to t. We want to express the given information and the required rate in terms of derivatives. So in terms of the derivative of the appropriate variable. And write an equation that relates the various quantities of the problem. If necessary, use the geometry of the situation to eliminate one of the variables by substitution. So sometimes we will have way too many variables and we will need to substitute some of them out of our function in order for this to make sense. The next one is we need to use the chain rule to differentiate both sides of the equation with respect to time. So this is going to be similar to when we did implicit differentiation. Whenever we took the derivative of y with respect to x, we differentiated the function of y normally, and then always multiplied by y prime, or dy dx, although we didn't often write it that way. In this section, we'll be doing it with respect to time. So we're always going to be getting a d something dt, or that variable prime if we use the convention that we're talking about, time. Lastly, we're going to substitute the given information into the resulting equation and solve for the unknown rate. So this next part that says warning, when we first start out, it's really easy to fall into this trap. A common error is to substitute in the given numerical quantities for quantities that vary with time too early. If we do that before we take the derivative step, which is right here, the second to last one, if we substitute in constants before we take the derivative, what's the derivative of a constant always? 0. So we will end up with equations that don't make sense if we substitute those constant values in too soon. Because if the quantity is changing with time, we have to wait till after we take the derivative to make that substitution. So then that's just our warning, and we'll see that as we go forward. Just be careful and don't substitute until after you've taken the derivative. All right, so let's take a look at example number 1. So example 1 states the following. The leg of a right triangle is growing at a rate of 3 centimeters per second. The other leg is constant with a length of 5 centimeters. How fast is the hypotenuse growing when the leg is 10 centimeters? All right, so we'll draw a picture to help us get started. And we have a right triangle. We know that a leg of the right triangle is growing at 3 centimeters per second. So I'm going to label using the standard labels for a right triangle, which is A, B, and C for the hypotenuse, right? Over on the side, I'm going to also write all of these quantities down. So I have A, I have B, I have C, and then I'm going to have their appropriate derivatives. So dA dt, dB dt, and dC dt. And then we'll fill in what we know. So we know that the leg of a right triangle is growing at a rate of 3 centimeters per second. And it's either one of the legs. I'm going to pick it to be A. If you made that leg B, you're going to get the same thing. So we have a rate. So the rate tells us that that is going to be the derivative. And it's growing at a rate of 3 centimeters per second. The other leg is constant with a length of 5 centimeters. Well, that's going to be our side B, and we know its length is going to be 5 centimeters. If it's constant, what is dB dt going to be? Well, the derivative of a constant is going to be 0. Then the last part says, how fast is the hypotenuse growing when the leg is 10 centimeters? So this leg, we're told the other leg is 10 centimeters. So that's going to go here as well, right? So we want to know, well, how fast is the hypotenuse growing? Well, growing is a rate of change, so we want dC dt. When we look at this, we know A, we know B, but we don't know C. Can we figure out what the value of C has to be? Sure. It's a right triangle, right? We can solve for C by using the Pythagorean theorem. So that gives us a squared plus b squared equals c squared, which is going to be 10 squared plus 5 squared is equal to c squared. So that gives us 100 square centimeters plus 25 square centimeters equals c squared. So that gives us 125 square centimeters equals c squared. We take our square root, and 125 is 25 times 5. So we take its square root. Square root of 25 is 5, and we get 5 square roots of 5. And the square root of centimeters squared is just centimeters. So we get C is 5 square root of 5 centimeters. So now we're finally ready to resolve this problem. So we want to find dC dt given these values. So we're going to need to use the Pythagorean theorem again as we do this step, because that's our model for this part. We need to use the chain rule to differentiate both sides of the equation with respect to time. So our relationship between a, b, and c is the Pythagorean theorem. So if we take our derivative of both sides with respect to time, the derivative of a squared is going to be 2a, and then by the chain rule, we're going to get a dA dt, or an a prime, plus when we differentiate b with respect to time, we get a 2b times dB dt is equal to the derivative of c squared is going to be 2c times dc dt. And the quantity that we want is dc dt. So we can solve the equation for dc dt by dividing everything by 2c. So those reduce out in each of these factors. The 2 reduce out. And finally, then dc dt is equal to a divided by c dA dt plus b divided by c dB dt. So now that we've taken our derivative, it is finally time to substitute in our known values. So we come back up here. A is 10, b is 5, and c is 5 square roots of 5. dA dt is 3, dB dt is 0, and dC dt is what we're trying to find. Well, let's start with this guy right here. So if dB dt is 0, we don't even really have to worry about this because 0 times anything is going to be 0, right? So we substitute in our values. So dC dt is equal to a divided by c. So that's going to be 10 centimeters over 5 square roots of 5 centimeters times dA dt. And dA dt is 3 centimeters per second. As I mentioned, this really isn't going to matter, but I'll plug it in just to be complete. So B is 5 centimeters over C, which is still 5 square roots of 5 centimeters, times dB dt, which is 0 centimeters per second squared because it's constant. So as mentioned, that whole term is 0. So now we notice our units, centimeters and centimeters, reduce out. 2 goes into 10 5 times. So we get dC dt is equal to 5 times 3 is 15 centimeters over 5 square roots of 5. Then those reduce a little bit more. We get 3 over the square root of 5 centimeters. Oh, that wasn't a 2. I'm a crazy person. Let's go back up. I reduced an S, not a 2. So this guy should have been 10 centimeters. So let's just re-reduce this. Let's just multiply it out. So 10 centimeters times 3 centimeters is 30 centimeters squared over, and in the denominator I'll just write it out, 5 square roots of 5 centimeters times S. So then things do reduce. 5 goes into 30 6 times. One of our centimeters reduce out. We get 6 centimeters over 5 and seconds. So this is a perfectly good answer. I know in the past they tell you to rationalize, and there's nothing wrong with multiplying the top and the bottom by the square root of 5 to get 6 square roots of 5 over 5 centimeters per second, but it's probably more telling to have a decimal approximation. So 6 times the square root of 5 divided by 5 gives us that the hypotenuse is growing at a rate of 2.68 centimeters per second, approximately. Okay, interesting. So what does that tell us? If we have a triangle where this side doesn't change length, but this leg is growing at 3 centimeters per second, the hypotenuse of the triangle is getting longer at the rate of 2.68 centimeters per second. Very, very interesting. All right, let's try our next example. So this one is an example of something that would not be physically possible for us to measure directly. So air is being pumped into a spherical balloon at a rate of 100 centimeters cubed per second. How fast is the radius of the balloon increasing when the radius is 25 centimeters? Okay, so we're going to use our imagination and pretend I can draw a sphere. So we have something that looks like this. And from the center of the sphere, to some point, we have a radius r. The things that we know about is we have a sphere, and we're told that air is being pumped into the balloon at a rate of 100 cubic centimeters per second. Well, 100 cubic centimeters is a volume. So that tells us that our rate is given in terms of a volume. So the model that we're probably going to need is that for the volume of a sphere. And what's our formula for the volume of a sphere? Perfect. So we get 4 over 3 times pi times the radius cubed. So that's our volume of the sphere. And now we need to write down a couple of things and try to figure out what we know. We have R, we have V, we have dr dt, and we have dv dt. So we're told that air is being pumped into the balloon at a rate of 100 cubic centimeters. So that's a volume per second. So 100 cubic centimeters over seconds. And then we're told how fast, or asked, how fast is the radius of the balloon increasing when the radius is 25 centimeters. And so then dr dt is what we want. So we could solve for v in this case, but since v is a linear function by itself, it turns out when we take the derivative, there's going to be no v's left. So we're not going to have to solve for it. If you do, it's not going to be a serious problem, but we're now ready to take our derivative. So we take our derivative d dt of both sides of our equation. So d dt of v, the derivative of v is 1 times the derivative of the inside, which is dv dt, is equal to, pi is a constant, so it comes out, the derivative of r cubed is 3r squared times the derivative of the inside, which is dr dt, by the chain rule. Yeah, there's a 4/3. Thank you. Came out with the constant. All right. So now we want dr dt. Reduce a couple of things out. We have dv dt is equal to 4 pi r squared dr dt. So we want to solve for dr dt by dividing by 4 pi r squared on both sides. So then we end up with dr dt is equal to 1 over 4 pi r times dv dt squared. All right. So now we can just plug in what we know. R is 25 and dv dt is 100 centimeters cubed per second. So we have 1 over 4 pi r is 25 centimeters squared times dv dt is 100 cubic centimeters per second. So we multiply all of these together and we get 100 over 4 pi. 25 squared is 625 times 625, and then our units are going to be centimeters cubed over centimeters times centimeters is centimeters squared times seconds. So 4 times 625 gives us 2,500. So we get 100 over 2,500 pi. And then here, the centimeters squared reduces with the 3 to leave just centimeters over seconds. Which makes sense because we're trying to find the rate of change of the derivative, or of the radius, which is its derivative, which should have units of velocity, which would be centimeters per second. So finally, 100 and the 2,500 reduced to give us 1 over 25 pi centimeters per second. So let's get a decimal approximation of that. So we get 0.0127, so forth. So it tells us that our radius is increasing by about 0.013 centimeters per second. So not very fast. But if you think about this situation, would it be possible to be standing inside this balloon and measuring its radius? No, not directly, right? So related rates give us the ability to make indirect measurements or observations of quantities that we may not be physically able to measure, as long as we know a relationship between those variables. So in our situation, we have our wall, we have our ladder. Looks something like this. I'll label this side A, this side B, and this side C. Making my chart, I have my A, I have my B, I have my C, and the possible derivatives are dA dt, dB dt, and dC dt. So our ladder is 10 feet tall, so we know C is 10 feet and rests against a wall. If the bottom of the ladder slides away from the wall at 1 foot per second, so that's this side, and it's moving away from the wall at 1 foot per second, so that means dA dt has to be 1 foot per second. We want to know, well, how fast is the top of the ladder sliding down the wall? So we want dB dt when the foot of the ladder is 6 feet from the wall. So that's when A is going to be 6. So we weren't given B or dCdt, but since the height of the ladder isn't going to change, it's always going to be 10 feet, dCdt is going to be 0 feet per second. And we can solve for B using the Pythagorean theorem. So a squared plus b squared is equal to c squared gives us 36 plus b squared is equal to 100. So we minus 36, and we get b squared is 64. Take our square root, so b has to be 8, so 8 feet. So now that we have all of our information, we can take the derivative of our model. So we take d dt of both sides, and that's going to give us 2a dA dt plus 2b dB dt is equal to 2c dC dt. And this time we want dB dt. So we minus 2a dA dt from both sides. And that leaves us with 2b times dB dt is equal to 2c dC dt minus 2a dA dt. And we divide everything by 2b to get dB dt by itself. So our 2's are going to reduce out, and we get c over b dC dt minus, the 2's reduce out here, a over b dA dt. So now we plug in what we know. A is 6, B is 8, C is 10, dA dt is 1, and dC dt is 0. So we know that this one's going to be 0, so this entire term is going to be 0. So we end up with dB dt is equal to 0 minus a divided by b, so 6 over 8 times dA dt, which was 1 foot per second. So this is going to, our feet reduce out, 6/8 reduces to negative 3/4 feet per second. So the top of the ladder is sliding down the wall at 3/4 of a foot per second. So notice we had the negative 3/4 in our answer, because as the bottom of this ladder moves away, since the hypotenuse is constant, B has to be moving down, right? So the sign tells us the direction that that piece was moving. So in example 1 and in the example 3 you try, the one you guys just did, we used the Pythagorean theorem because our situation gave rise to right triangles. It's possible to have situations where we will not be given a right triangle. So let's draw a picture to go along with example 4. So at noon, ship A and ship B leave the same place. Ship A is sailing southeast at 35 kilometers per hour, and ship B is sailing west at 50 kilometers per hour. How fast is the distance between the two ships changing after 3 hours. So just to remind us of our cardinal directions, we have north, south, east, and west. So we're going to start with ship A and ship B here. Ship A is sailing south and east. So that's ship A. And ship B leaves the same place and is sailing west. We want to know, well, how fast is the distance between these two ships changing after 3 hours? So, if I call this side little a, I call this side little b, and I call this side little c, using the same convention for naming non-right triangles, where side A is across from what would be angle A and so forth, we're going to get this. Okay, we need to figure out some things, what we know and what we want. So let's start with A and dA dt, B and dB dt, and C and dC dt. So what do we know? Ship A is sailing southeast at 35 kilometers per hour for 3 hours. So that means this side right here is going to be 3 hours times the rate, which is 35 kilometers per hour. So that's going to be 105 kilometers. 3 hours. So the hours reduce out, and we get 105 kilometers. Ship B is sailing west at 50 kilometers per hour, so that's 3 hours times 50 kilometers per hour. So we're going to get 150 kilometers. I'm putting all of those in the wrong place, so let's just move them. Sorry, I was calculating the distances, not the derivatives. The derivatives are the actual rates. So the length of that side, on the length of this side, that's just a mess, isn't it? So it really should have looked more something like this. Because we were given the rates, which we'll fill in now. So dA dt, dB dt, and dC dt. So to figure out the distance, we knew how fast each of them were going and for how long. So we just multiplied 3 hours times 35 gives us 105 kilometers. 3 hours times 50 kilometers per hour gives us 150 kilometers. That one should go up here. 3 hours times 50 kilometers per hour gives us 150 kilometers. We don't know C yet, but we do know these rates. So this is going to be 50 kilometers per hour. Our rate here is 35 kilometers per hour. dc dt we don't know. And c we don't know. We do want to know, well, how fast is the distance between the two ships changing? So we want this value. And similar to the right triangle examples, we don't know one of the sides of this triangle. So we're going to have to solve for that missing piece. So there's one other piece of information that is implied that is important. So in these types of problems, when they say it's sailing southeast, they mean exactly southeast. And what I mean is if we were to think of this right here, if it's sailing exactly southeast, what would the measure of this angle have to be? Well, to go from south to west would be 90 degrees, right? And if you're going exactly southeast, that means you're going halfway in between these two things. So if that whole angle is 90, what would half of the angle have to be? 45. So the entire angle would be 135 degrees, or its equivalent in radians would be 3 pi over 4. So now, armed with this information, we can use the law of cosines to find c. So we will use the law of cosines to find c. And the law of cosines is c squared is equal to a squared plus b squared minus 2ab times the cosine of the angle c. So this is the generalization of the Pythagorean theorem that works for any triangle. So first things first, let's go ahead and solve for c. To make my life a little bit easier, I'm going to save some of these values into my calculator. So I'm going to go 150, and I'm going to store that as a in my calculator. So I go 150, hit my store button, and then go alpha A. I'm going to go 105, hit my store button, and put that in as B. Then c squared is equal to a squared plus b squared minus 2ab times the cosine of 3 pi divided by 4. So that's c squared, and I want c, so I'm going to go second square root answer, and I get this as my value, and then I'm going to store that in my calculator as c, because I'm going to need that later. So I'll write down an approximation about 236.2 kilometers, and then I'm just going to take note that it's in my calculator as c. And I'll just use the exact value in my calculator. Alright, so now we have all the parts that we need. So now we have our law of cosines again, and we solved for c using our calculator. We now have to take the derivative of this, and just to remind me that this was the angle c, I'm going to actually just put my angle in to remind me that that's a constant, right? Because I'm not going to be taking the derivative of the cosine function, because this piece right here is constant. And in fact, if you really want to, what is the cosine of 3 pi over 4, you should get negative square root of 2 over 2, right? So we could figure out what that is if we wanted to. So we take our derivative, and we get 2c dc dt is equal to 2a dA dt plus 2b dB dt, so just like we normally had, minus, but here's where it gets interesting. In this next part right here, I have a negative 2a times b, right? So I have negative 2. I'm going to pull out my negative square root of 2 over 2. But on this part, where I have a times b, how are these two things connected? Multiply, right? And they're both functions of time, so I have to use the product rule. So the product rule is going to be gf prime plus fg prime. So in this case, it's going to give me b times dA dt plus a times dB dt. And that's just gf prime plus fg prime, where a is f and b is g, right? That's our product rule. So we've taken our derivative. What is it we're trying to find? We want dc dt, right? So luckily, we now just divide everything by 2c. To facilitate making this easier to type into my calculator, all of them have a common factor of 1 over c, right? So I'll factor it out, that way I don't have to type it 10 times. And then I will have a dA dt plus b times dB dt minus, a minus makes it plus, square root of 2 over 2 times b dA dt plus a dB dt. So basically what I did here is, since every factor had a c in it, I just factored it out in front, right? So that way I'll only have to type it once when I go to put all of this into my calculator. All right, so now it's calculator time. Well, I have 1 over c, which I saved in my calculator, times a times dA dt. So we go back up, and what's dA dt was 50. Yeah, they're not going to all fit. So dA dt was 50, so times 50, plus times b, dB dt was 35, plus the square root of 2 over 2 times parenthesis b, and dA dt was 50, plus a times dB dt, which is 35, We then close our parentheses, close our second set of parentheses, and we press enter. Calculator thinks for a moment, and we get the value . 78.73. So we get that dc dt is approximately 78.7 kilometers per hour. All right, so a couple of notes on this. When we have a product of variables that both change like this, we still have to use our product rule, right? And with some of these problems, if there's enough variables, I find it easier, like what we did here, to save things into my calculator to use later. Because if you try running with all of those numbers, it gets a little crazy. And there's a lot of stuff to type in and keep track of. All right, so example 5. So first thing I do need to note, I had already printed the notes when I noticed that this part was missing right here. So your version doesn't have when the height is 2 meters. That is important to the problem. All right, so a cone-shaped tank with a radius of 5 meters and a height of 8 meters is being filled with water at a rate of 3 cubic meters per minute. How fast is the height of the water increasing when the height is 2 meters? So in this situation, we definitely need to draw a picture. So we got a cone tank that looks something like this. We know that its radius is 5 meters, and we're told that its height is 8 meters. I'm sorry, what? So what's going to make this situation a little bit difficult is, now let's imagine as we're filling this tank up, as the height changes, the radius of the tank is changing, right? So when you first start pouring water in the bottom of that cone, it's going to fill up very, very fast. But the wider the cone gets, the more water it's going to take to fill it up, right? So we're going to have to figure out some information about this situation. So once again, we have our rate right here, which is in meters cubed. So that is a volume. So that suggests a good model might be a volume formula. So what is the volume formula for a cone? Perfect. So we have V is 1/3 pi r squared times h. So fun fact about these, if you aren't aware, the volume of any cone, and when I say cone, I mean the general cone, is always 1/3 the area of the base times the height. So the base of this cone is a circle, and what's the area formula for a circle? Pi r squared, right? So if you had a square base, it would be 1/3 the area of the square base times the height. If you had a triangular base, aka a prism, you would use the area formula for the triangle, or so forth. So that volume formula in its most general form is 1/3 the area of the base times the height. And for those of you that are going on to Calc 2, you'll prove that formula using calculus instead of traditional geometry to resolve that. All right. So let's go ahead and see what we know and see what we can find. So we have our volume, which depends on the radius and the height. So we have R, we have H, and we have V. And then we're going to have dr dt, dH dt, and dV dt. So let's figure out which of these we know. So the one thing we have to be careful about is we're talking geometrically about the cone, but when we're talking about the rates, we're actually talking about the water inside the cone, right? Because does the cone's shape change at all? No, the cone's always going to be 8 meters. It's always going to have a radius of 5 meters, and it never changes. The only thing that's changing is the amount of water in the cone. So when we're talking about this, we're talking about the water. So in this case, there isn't a ton that we know. We know that when the height of the water is 2 meters, so when h is 2 meters, we want how fast is the height of the water increasing. So this is what we want. We know that the tank is being filled at water, or with water, at a rate of 3 cubic meters per minute. We don't seem to know anything about R, and we don't know anything about V, right? So let's go ahead and label these other parameters that we don't know here. So we're going to have to use some geometry to help us out. So there are 2 different ways we can resolve this conundrum that we have. Method 1 is going to be geometry. And method 2 is going to be algebra. So both of these are useful. And in some situations, one is going to be superior to the other. In this case, I think they work about the same. So let's talk about the geometric method first, which is if we were to take a cross-section of this cone, so imagine cutting it on one of the diameters of the cone. If you cut it in half and laid it down, so let's do 2 cuts, it would look like this. So we cut the cone in half on a cross-section and then cut it in half perpendicular again, and we would get a triangle, right? Because one of the cross-sections would be a triangle that looked like this part, and then if you cut it in half again down this line, you would get another triangle. So we know some information then. This is 8, and the radius is 5. We are trying to find some information about what we call R and H, right? When we write it this way, you may notice that we actually have some similar triangles going on here, right? So 2 triangles are similar. if the ratios of their corresponding sides are equal. So two triangles are similar if the ratios of their corresponding sides are equal. We know from geometry that these are similar by angle, angle, angle. Because if we look in our triangle, well, they share that angle. Both of these are right angles. And if they have two angles that are the same, then their third angle automatically has to be the same, right? Because you calculate the third angle by subtracting off the first two from 180. So by angle, 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 these two triangles are similar. So then, since they're similar, the ratios of their sides must be equal. So then, if I do small over big, I'm going to get that h, which is this small side, over the full side, which is 8, has to be equal to r divided by its corresponding side, which is 5. So I can then solve this for r by multiplying both sides by 5. So r is equal to 5/8 h. So that gives us a relationship between r and h, right? So the radius will always be 5/8 of the height. So method 2 is the pure algebra way. So using that same diagram in terms of r and h, if we did something similar, if we think of our ordered pairs as r comma h, at this point, what would our ordered pair be? Well, when I wrote my ordered pair backwards, it's h comma r. Not that it would matter, we'd just have to solve for the other variable. But at this point, when the height is 0, what does the radius have to be? 0, right? And when I'm all the way at the top, at this point right here, when my height is 8, what is the corresponding radius? Well, what's the radius of our thing? 5, right? So then I could find my slope, which is 5 minus 0 all over 8 minus 0, which gives me 5/8. And then it contains the origin. So my equation is r minus 0 equals m times h minus 0. But m is 5/8. So simplifying, we get r is equal to 5 over 8h. So same thing, right? One using algebra and coordinatizing the relationship between the two things. The other is using geometry and the fact that we had similar triangles. Both methods are valid. Whichever one makes you happy is the right way to do this problem. So either way, we now know that r is 5/8 of h. So inside of our formula, we have v is 1/3 pi r squared times h. But we know r is the same as 5/8 h. So if I substitute that into my formula, I get the following, right? So multiplying this out, 5 times 5 is 25 times pi times 1, so that's 25 pi. 8 times 8 is 64, and 64 times 3, I'm not trusting myself this morning. 64 times 3 gives 192. And h times h is h squared times another h is h cubed. So by using that relationship between the variables, our volume is now expressed only as a function of height. So in terms of full disclosure, you could have used the chain rule on the original formula, taken the derivative on this, and then you would have had to use the product rule as well, and substituted everything in. It's a much longer process, but it does work. So we get this nice formula to finally take dv dt. So dv dt is 25 pi over 192. The derivative of h is going to be 3h squared times dh dt. So 3 times 25 is 75 pi h squared over 192 times dh dt. So now, we've been doing this for so long I almost forgot. What is it we're trying to find? We want dh dt, and what is it we know? dv dt. Perfect. Because those are the only two things in our equation. So we have dv dt is equal to 75 pi h squared over 192 times dh dt. So we divide by 75 pi h squared over 192 on both sides. And that gives us that dh dt is equal to, multiplied by the reciprocal of our fraction, so 192 over 75 pi h squared times dv dt. All right, so from here, we plug in what we know. So our dv dt is 3 meters cubed per minute. So we get 192 over 75 pi. Our height was 2 meters times so our height was 2 meters times 3. This. Let's put that all in our calculator and see what we get. So we have 192 over 75 times pi times 2 squared times 3. And we get 0.611 and some change. So our height is going to be approximately 0.61 meters per minute. All right, so that completes our penultimate example. It's now time for the grand finale, so example number 6. So a lighthouse is located on a small island 2 kilometers away from the nearest point P on a straight shoreline. And the lighthouse makes 4 revolutions per minute. How fast is the beam of light moving along the shoreline when it is 1 kilometer from P? All right, so let's draw a picture of this situation. So it says a lighthouse is located on a small island 2 kilometers away from the nearest point P on a straight shoreline. Here's our point P. Here's our lighthouse. We know that this distance is 2 kilometers. And we have our straight shoreline. We know that the lighthouse makes 4 revolutions per minute. How fast is the beam of light moving along the shoreline when it is 1 kilometer from P? So I'm going to choose to put it up here. If you do it down here below, you're going to get the same answer. You're going to draw the same triangle just with a different orientation. So we then have our light beam is coming from our lighthouse, and it's on the shore here. As it spins around, that beam of light hits the shore and moves along this straight line segment. We are told that this distance right here is 1 kilometer. And we want to know, well, how fast is the light beam moving along the shore? So at first glance, we might think that this is similar to the ladder problem that you guys did earlier. And it is in a certain sense that this is a right triangle, but we're given a very different set of information. What is our rate that we're given? 4 RPMs, right? So 4 revolutions per minute. So that tells us that the lighthouse rotates 4 times per minute. So in terms of trigonometry, what type of measure is 4 revolutions per minute? Well, a revolution is an angle, right? So that tells us it's going 2 pi radians 4 times per minute, or 8 pi radians per minute. So our rate that we're given is an angle. So this is an angle over minutes, right? So that means we have theta as one of our unknowns. So theta, its corresponding rate is d theta dt. And then we want this distance right here. Well, I'm going to label the sides of my triangle A and B once again. So then I have A, and I do know A's value is 1 kilometer. And I have B, and it's going to be 2 kilometers. Then I have dA dt, and I have dB dt. So we need to figure out our corresponding rates for each of these. So one of them is, we're told that d theta dt is 4 revolutions per minute. But we can't use 4 revolutions per minute in a math problem. We always have to convert all of our angles to radians. So 1 revolution is 2 pi radians. So I'm going to have 2 pi radians equals 1 revolution. So 2 pi radians over 1 revolution. Our revolutions are going to reduce out, and that is 8 pi radians per minute. So our rate for d theta dt is 8 pi over minutes. So now dA dt, oh, well, that's how fast the light is moving along the shoreline. That's what we want. And what's our dB dt going to be? Well, does the distance from the lighthouse to the shore ever change? No. So that rate is going to be 0 because the lighthouse's distance from point P is fixed. It's always 2 kilometers. So the one thing we're missing is theta. So theta would be this angle right here. Well, what 2 sides of that triangle do we know? Opposite and adjacent. So the tangent of theta is going to equal to opposite over adjacent, which is A over B, right? So when the distance from the lighthouse is 1 kilometer, so when A is 1, we know B is 2, we can solve for theta by having tan theta is equal to A over B, so 1 over 2. So taking the inverse tangent of both sides, we get theta is the inverse tangent of 1/2, right? So now we are finally ready to take our derivative. So what's our model? Well, this is our model, right? That's what relates our variables. The tangent of theta is equal to A divided by B. So we take our derivative, d dt of tangent theta is equal to d dt of A divided by B. So on the left-hand side, the derivative of tangent is secant squared. So we're going to get secant squared theta times d theta dt is equal to, and now we need to take the derivative of this side. Well, we have A and B. How are they related? Quotient. So it's going to be quotient rule, right? And if that's the case, we have F, and we have G. Our F is A, our G is B, so then F prime is dA dt, and G prime is dB dt. So our quotient rule is G F prime, so B times dA dt minus FG prime, so that's A dB dt, all divided by G squared. So then we know that dB dt is 0, right? So then this is going to reduce to B dA dt divided by B squared. And then b squared divided by b, we're going to get 1 over b dA dt. So something that's come up a couple of times, and I've formally handled it both times by just using the appropriate rule, product rule, quotient rule. In this case, we could have avoided the quotient rule. Why is that? What do we know about b? What's dB dt? 0. So b is a constant. So it's worth noting we knew b was a constant. So we didn't need to use the quotient rule. So if we rewind back to this point, d dt, tangent theta, is equal to d dt of a over b. If we know b is a constant, what does that mean we can do? It just comes out of the derivative, right? So this would be the same as 1 over b times dA, I'll write it out in steps, d dt of a, because b is a constant. So then when we take our derivative, we still get secant squared theta d theta dt is equal to b. And then what's the derivative d dt of a? Well, a is 1 times dA dt. Well, notice, is that exactly the same thing we got after doing the quotient rule? And indeed, the answer is yes, right? We got the exact same thing because the derivative was 0. So the moral of this story is if you're not sure, just use the full rule. It'll get you the right answer. But if you know something's a constant, you can treat it as such before taking the derivative. But remember, if it's not a constant and you do this, it's going to mess up the problem. So if you're not sure, just wait till the last step. But you can save yourself a little bit of work by doing them this way. Okay, so now back to our regularly scheduled problem. What is it we want? dA dt. So we're going to multiply both sides of this equation by b. So we have b times secant squared theta d theta dt is equal to dA dt, which is what we want. So we need to plug in our values, but let's do this. So we have theta, or d theta dt is 8 pi per minute, and theta is the inverse tangent of 1/2, and b is 2. So we're going to have 2 times the secant squared of the tangent inverse of 1/2 times d theta dt, which is 8 pi per minute, is equal to, and I'll put the dA dt over here. So we need to simplify this up a little bit. Well, we'd already drawn the triangle, so tangent is opposite over adjacent, so that's 1, 2, and we could figure out the hypotenuse. So 2 squared is 4 plus 1 squared is 1, so this is the square root of 2 squared plus 1 squared, so that's the square root of 5, right? So then we start filling in our values. We have 2 times the secant squared. Well, what is secant? 1 over cosine. So cosine is opposite over, or adjacent over hypotenuse. So secant is hypotenuse over adjacent. So we're going to get the square root of 5 over 2. squared times 8 pi and we get 2 times 5 over 4 times 8 pi. So some of these things reduce. 2 times 5 times 2 gives us 20 pi. And it's going to be kilometers per minute. And just to be explicit, the b was 2 kilometers. And we get that as our answer. So, a couple of things I do want to mention. I worked out the trig by hand. You don't have to, right? So our calculator doesn't have a secant button, so we do have to do the 1 over the cosine part, right? Because it doesn't have secant. So it's 1 over cosine, and then you would have to go second to get your inverse tangent of 1 divided by 2. And we get the value, this, and then we need to square that because it was squared. And we get 0.125, which exactly matches the 5 over 4 that we calculated when we did this, right? So I'll often do a lot of computations by hand. You can just shove it all into your calculator, right? I do want you to be aware of, because sometimes the hand calculations do come in handy depending on what we're trying to do. But that gives us our rate, which we can now calculate as 20 pi. So 20 times pi is going to give us 62 kilometers per minute is how fast that light beam is moving along the shoreline. So if you wanted to, if you divided that by 60, it would convert it from kilometers per minute to kilometers per second. So it's going about a kilometer per second along the shoreline. So it seems pretty reasonable if you've ever watched a lighthouse do its thing. All right.